There's a large, serious body of work on machines doing mathematics. Conjectures, definitions, proof search, elegance. It's some of the most interesting technical writing being produced right now. And it was written almost entirely without an adversary in the room. That's not a criticism, it's a description of the frame. And this season is what happens when you put one in. And the reason we are doing a deep dive on these specific sources today is because, well, the tech industry is basically about to take these brilliant but completely defenseless math machines and just plug them directly into our most sensitive network-attached infrastructure.
Yeah.
And our mission today is to figure out exactly what breaks when they do that.
It's a really critical mission because, I mean, we're looking at this brilliant body of literature on machine mathematics. Like you have artificial intelligence generating these incredibly complex conjectures or formalizing proofs, exploring these vast abstract spaces.
Right.
And honestly, the papers, they read beautifully, but they describe a reality that does not actually exist in the world of deployment.
Right, because this entire body of literature, all these incredible models, they reason about idealized systems.
Right.
They exist in this sort of vacuum, like a pristine whiteboard where the math just works and the rules are always followed and the environment is just perfectly cooperative.
Yeah, that is the core issue, because on a whiteboard, these ideas are elegant.
Beautiful even.
Exactly. But when these systems leave the lab, they are going to be containerized, they will be credentialed, they'll be network attached, multi-tenant, and most importantly, they will be adversarially exposed.
Yeah.
If we take the capabilities described in this literature and deploy them without applying a strict security lens, we're essentially handing over highly capable, highly vulnerable systems to literally anyone with an internet connection.
So what does this all mean for the researchers? I mean, if these AI researchers and mathematicians weren't writing for security engineers, which is fair, I mean, that wasn't their job, did we just throw their work out? Like, did they build something completely useless because it lacks a threat model?
I wouldn't go that far. And that's a really crucial distinction to make right up front. Because this isn't a rebuttal of the capability literature. We aren't saying the AI researchers are wrong about what their models can achieve mathematically.
Right.
We need to view this as a translation.
Yep.
Most of the theoretical claims they make absolutely survive contact with the threat model. The capability remains, but its implications shift drastically when an active adversary enters the room.
Okay, let's unpack this, because to bridge that gap, we need a disciplined way to translate those theoretical claims into actual security realities. And our sources provide this translation matrix, which is like a way of mapping the theoretical object the AI researcher is building to what it actually becomes once it ships into a hostile production environment.
Exactly.
Let's start with the foundation. So in the math literature, everything starts with proofs, axioms, and definitions. In a vacuum, an axiom is just a self-evident truth. But what happens to an axiom when you put it on a server?
When you move from a theoretical proof to a deployed system, those proofs and axioms and definitions, they become hard-coded system invariants. They become what security engineers call the trusted computing base, or the TCB.
The TCB, right?
Right. So the TCD is the bedrock of what the system assumes to be absolutely true and structurally secure. Like if a math AI assumes that A equals A to solve a theorem, the deployed system assumes that the user with this cryptographic token is the administrator.
Oh, I see. But in the real world, the TCB is exactly what an attacker targets, right?
Yeah.
Because if you can compromise the axiom, the whole proof just falls apart.
That's the translation. The AI researcher views an axiom as a sturdy foundation to build upon, but the security engineer views the TCB as the single point of failure that must be defended at all costs.
Wow, yeah.
Because if your AI's mathematical reasoning assumes the integrity of its environment, an attacker will simply compromise the environment. They invalidate the axiom and make the AI behave maliciously while mathematically proving it's doing the right thing.
Which brings up what happens when the math gets hard. The capability literature talks a lot about complexity, undecidability, and unbounded search.
Yes.
And to a mathematician, unbounded search just means the AI is going to keep turning over rocks, right? Exploring infinite permutations until it finally cracks a difficult theorem. Like, it takes as long as it takes. But in a multi-tenant cloud environment, unbounded search just sounds terrifying.
Because it is mechanically identical to a denial of service attack.
Oh, man.
In the security realm, complexity and unbounded search translate directly to resource exhaustion. Let's look at the causality here.
Okay.
If an AI is designed to search an unbounded space to resolve a query,
Yeah.
an attacker doesn't actually need to break into your server. They just need to intentionally feed the system an unsolvable paradox.
Oh, wow. So they deliberately ask a question that has no answer.
Yes. Because the system's architecture dictates that it must search until it finds an answer. It will eat up 100% of your server's compute memory and bandwidth trying to solve the attacker's paradox.
So it'll just lock out every legitimate user.
Exactly. The researchers built a tireless worker, but the attacker turned that tirelessness into a localized blackout. That is how a brilliant mathematical feature becomes verification exhaustion. The checker fails open, and the system just falls over.
But to solve those hard problems, the AI sometimes has to change its perspective. Like, the literature talks about state space expansion and abstraction shifts.
Right.
Like, if you can't solve a problem in 2 dimensions, the AI learns to project it into 3 dimensions to find a shortcut. Mathematically, that's genius, but in a deployed system, aren't we usually trying to keep things in a very specific, limited box?
We are. We call that box a sandbox, or a secure enclave. And this is where the translation gets particularly stark. Because expanding the state space in theory is great for finding novel math proofs.
Sure.
But in practice, finding a novel dimension that the system wasn't previously monitoring is the literal definition of a side channel or a sandbox escape.
Can you give me an example of how that actually works? Like, how does a math concept translate to stepping out of a sandbox?
Sure, think about row hammer attacks on physical memory or cache timing attacks.
Okay.
The software sandbox assumes the state space consists of logical memory addresses and permissions. That's the two-dimensional view.
The rules of the software.
Exactly. But the attacker expands the state space to include the physical proximity of silicon chips or the microscopic time delays in CPU processing.
Oh, wow.
The defender wasn't modeling the physics of the hardware. They were only modeling the logic of the software. So the attacker expanded the state space, shifted the abstraction, and bypassed the security controls entirely. An AI trained to aggressively expand its state space to solve problems will just naturally discover these escapes.
Which perfectly sets up the last major translation from the sources. And it's one of the most persistent problems in software history, which is theoretical equivalence and representational choice.
This is perhaps the most subtle and dangerous translation. The mathematical literature frequently treats different representations of the same underlying concept as theoretically equivalent.
Right, like how cancel my subscription in natural language means the exact same thing as an API call structured as delete user account.
Yeah.
In theory, the AI assumes these 2 representations are perfectly equivalent.
But assuming 2 representations are strictly equivalent in a deployed architecture is exactly where the semantic gap opens up for exploitation.
Yeah.
In security, this translates to translation layer, friction parser differentials, and confused deputy attacks.
I really want to break down that confused deputy concept because it's so fundamental to how traditional hacking works.
Okay.
So let's stick with that API example. You have a policy engine, basically an AI that reads a user's natural language request. And then you have a runtime engine that actually executes the structured code. In a normal operation, I say cancel subscription. The policy AI says that is a benign authorized action, and it hands the delete command to the runtime.
And that works perfectly when the user is honest. But what if the user crafts a prompt that the natural language AI interprets as cancel my subscription, but due to a slight quirk in how the text is formatted, the runtime engine parses it as a command to dump the entire user database?
Because they are using 2 different parsers. Like parser A sees one thing, parser B sees another.
The entire history of security engineering tells us that the gap between 2 representations of the same thing is where the exploits live.
Wow.
The policy engine authorizes the action based on its understanding of the natural language representation. It essentially stamps a seal of approval on the request. Then the runtime engine executes what it parsed from the structured representation.
And when those 2 understandings diverge, you have a confused deputy attack.
Exactly. The AI acting as the deputy was confused into using its high-level privileges to execute a malicious action. And you know the worst part?
What?
The audit log will say the request was totally fine because the policy engine genuinely believed it was approving a subscription cancellation.
The system did exactly what it was designed to do, but because the attacker exploited the space between those 2 representations, the outcome is catastrophic.
Yeah.
Which brings us to a really stark conclusion from the sources. Like, if you have a capability proposal that has no threat model, you aren't just producing a neutral design that happens to be missing a few security patches. You are shipping a design pattern whose first competent implementation is inherently an attack platform.
It is a very uncomfortable reality for the field. It's not that the design is benign but weak. It's that the architectural structures required for advanced mathematics are fundamentally dual use.
Right.
If you don't bound them, they weaponize by default.
Which leads us to a really tricky problem. Because it seems like the exact same features we want the AI to have are the exact same features an attacker wants to use against us. Like, capability is not indexed by intent.
What's fascinating here is how clearly this overlap manifests when you look at specific mechanisms. Let's look at the features the machine mathematics literature is desperately trying to cultivate. They want a model capable of cross-domain bridging. That's the ability for an AI to take a concept from, say, topology and apply it to an unsolved problem in algebra.
That's the holy grail of intelligence, right? Making connections across completely disparate fields.
It is. But let's apply our security lens.
Right.
What is the mechanical action of cross-domain bridging?
Pulling things together.
Right. It is pulling seemingly unrelated, isolated pieces of information from different compartments and composing them into a new powerful output. From a security perspective, cross-domain bridging is literally an aggregation attack.
Because an attacker doesn't usually just break down the front door. They find a low-level credential in a marketing folder, they combine it with an abandoned script in a developer repository, and suddenly they have lateral movement across the network.
Exactly.
The AI pulling math concepts together uses the exact same cognitive machinery as an AI aggregating harmless data points into a lethal exploit payload.
Precisely the same machinery. Let's look at another one. The researchers want context refresh. When an AI goes down a rabbit hole trying to solve a proof and gets stuck in a loop of errors, they want it to be able to wipe its slate clean, forget the unhelpful context, and start fresh.
Wait, I can see where this is going. Because if the AI wipes its context, it doesn't just wipe the bad math.
It wipes the safety state. Context refresh is mechanically a safety state reset. Think about how modern AI safety works. It often relies on a conversational provenance.
Like the history of the chat.
Yes. As a user asks increasingly sketchy questions, the model's hidden state accumulates refusal decisions and escalating risk signals. The safety enforcement lives in that context.
Right.
If you give the model the architectural ability to deliberately erase its context to help its math performance, you've just provided a first-class, built-in safety control bypass.
So an attacker just triggers the context refresh right before asking for the exploit code. The model forgets it was just suspicious of the user and happily complies. Okay, what about systematic entropy injection? Because the literature suggests this is how you help an AI get unstuck from local minimums. You inject a little randomness, a little chaos to force it to find creative out-of-the-box solutions.
Injecting systematic variations into an input to explore edge cases and bypass expected constraints is known in the security world as fuzzing.
Oh, fuzzing, right.
When applied to an AI model to bypass its alignment training, it's mechanically identical to best-of-N jailbreaking.
Which is what exactly?
You spawn multiple decorrelated framings of a malicious request. Most of them will be caught by the safety filter. But because you injected entropy, one of those creative variations will slip through. The one that clears the filter is the output you use. It's a semantic fuzzer.
So it's just the same object relabeled objective, and the underlying reason for this is so fundamental, right? The computational substrate, the learned representations, and the search algorithms operating over those representations, it's entirely objective agnostic.
Yeah.
The machine does not know your intent. It doesn't know if it's searching for a beautiful, elegant mathematical proof that will win a Fields Medal, or if it's searching for a zero-day exploit in a hospital's container architecture. It's just searching.
The mechanism does not know which reading you intended. And this presents a severe limitation on how we build defenses. If the features that implement cross-domain mathematical analogy rely on the exact same neural pathways and computational structures as the features that implement dangerous knowledge composition, then there is no free lunch.
Meaning you can't just surgically remove the bad stuff with a quick software patch.
You cannot easily filter out the attack capability without simultaneously destroying the mathematical capability. If you try to aggressively fine-tune the model to never aggregate dangerous information, you will fundamentally degrade its ability to connect disparate mathematical concepts.
They're all tied together.
It's a package deal. The cognition required for brilliance and the cognition required for exploitation are structurally entangled.
Here's where it gets really interesting. If we can't just filter out the bad intent, because the AI doesn't understand intent, it only understands the task, how do we actually engineer systems that are safe?
Right.
We have to figure out how to measure the cost of defense. And the sources introduce a brilliant conceptual tool for this called the price of benignity. Let's unpack that.
The price of benignity is one of the most powerful analytical tools for bridging this gap.
Yeah.
To understand it, you have to look at what these AI architectures were originally optimized to face.
Mm.
Every proposal in this capability literature was optimized against nature.
Wait, let me push back on that. By nature, you don't mean a peaceful walk in the woods.
No.
Nature can be highly destructive, right? Like hardware fails, cosmic rays, flip bits in memory networks, drop packets. Isn't that a threat environment?
It is a hazard, but it is not an adversary. That is the critical distinction. Nature is stochastic. It produces noise errors and inefficiency.
Hmm.
But nature is indifferent. A cosmic ray might crash your server, but nature doesn't read your source code to calculate the exact microsecond to strike a specific transistor in order to bypass your authentication check.
Right.
Nature doesn't have read and write access to your environment's reward specification. Nature isn't trying.
Okay, I see. Nature is chaotic, but it doesn't have an agenda.
But when you deploy this mathematical system, you aren't facing nature anymore. You are facing an active, intelligent adversary. An adversary is trying.
Yeah.
When you take the exact same architectural proposal and optimize its performance against an adversary instead of nature, the optimum point of performance moves. Sometimes it moves a little, sometimes it collapses entirely.
So the price of benignity is basically the performance tax. It's the mathematical power you have to give up when you switch from operating in a natural vacuum to actively defending against an attacker.
That is precisely it. It is a quantifiable metric. It is the performance an architecture must sacrifice when you replace nature with an adversary drawn from a bounded set. And that concept of a bounded set is doing a monumental amount of heavy lifting here.
Let's pull on that thread. What happens if we don't bound or limit the adversary in our models? Because the flagship proposal in a lot of this literature is unbounded autonomous exploration.
Yeah.
The dream is to let the AI loose in a formal mathematical library unconstrained to just explore and find novel theorems forever. What is the price of benignity if the adversary is unbounded?
If the adversary is unbounded, the metric returns infinity.
Infinity. So the system just breaks.
The system mathematically and practically collapses. Let's look at the causality. If you have an unbounded adversary, that means the attacker has unmonitored dwell time and arbitrary write access to the environment. If you leave an optimizer running unattended for a decade with no bounds, and an attacker can subtly influence that environment, perhaps by poisoning the data it learns from or altering the axioms it relies on, there is no lower bound on the damage. They can steer that infinite search power directly into your core infrastructure.
Wow.
An unbounded metric is not a metric at all. It is a guarantee of systemic failure.
So if you can't bound the adversary, the architecture is dead on arrival for deployment.
That is the admissibility criterion that falls out of this entire analysis. An architecture is admissible only if its adversary set is bounded by construction. If you cannot draw a definitive box around what the adversary is mathematically capable of doing within the system, you cannot safely deploy the architecture. Full stop.
And most of these proposals haven't done that.
Most of the proposals in the capability literature have never been asked to meet that criterion because they were built for the whiteboard, not the war zone.
Okay, before we go any further, I need to do a status check. We've been talking a lot about how these AI capabilities map perfectly to attack capabilities like cross-domain bridging being the exact same thing as an aggregation attack.
Yes.
But for the listener who is following this closely, we need to draw a very hard line between what is a proven empirical fact and what is a highly educated hypothesis.
This raises an important question of epistemic status. We must be meticulous here. In that earlier discussion, we talked about the overlap between beneficial capabilities and malicious capabilities. The core claim is that the representational structures inside the AI's neural network that handle good mathematical analogy are the exact same structures that handle bad exploit aggregation. We need to be very clear that structural overlap is right now a conjecture.
Right. The sources are explicitly careful about this. They mention a proposed experiment to prove it involving something called the Jacquard overlap in sparse autoencoders. Let's demystify that for a second.
Sure.
For the listener who hasn't been deep in neural network architecture lately, think of a sparse autoencoder like a prism. When an AI processes information, it's a dense, tangled beam of light, like millions of neurons firing at once. If you shine that tangled light through a sparse autoencoder, it splits it into distinct, readable colors or features that a human can actually understand.
That is an excellent way to conceptualize it. The autoencoder forces the neural network to isolate specific concepts. The Jacquard overlap is a mathematical way of measuring how much two sets of features share in common.
So the conjecture is that if you use this prism to look at the features firing when the AI solves a math analogy, and then you look at the features firing when it builds a cyber exploit, you will see a massive Jacquard overlap. It will be the exact same colors shining through the prism.
Yes, it is a highly motivated conjecture, and they have laid out a clear, measurable experiment to test it. But it is not currently a published, proven empirical result. It is a prediction about what we will find when we run the math.
And it's so critical to mark that line between a strong argument and a published empirical measurement, especially in security engineering. Like, if we treat hypotheses as unquestionable facts, we end up building massive, expensive defenses for ghosts while ignoring the actual holes in the wall.
The differentiator for this entire body of work is maintaining those fragile hedges. We are describing structural exposures based on architectural translations. We must always separate what is shown from what is argued.
Which brings us to the practical reality. We've gone deep into the translation matrix, the terrifying implications of unbounded search, the price of benignity, and the dual-use symmetry of cognitive features. But for the listener who is building these systems or managing the teams deploying them and has to go back to work on Monday, what is the actionable takeaway? What do they actually do with all of this theory?
The primary directive, the most impactful, actionable step you can take on Monday morning is this. Write down your adversary model and date it.
Write it down and date it. Notice you didn't say write down the threat model for a specific piece of software. You said the adversary model.
Correct. The adversary model is foundational. You need to define in writing exactly what the adversary can read, what they can write, what they can influence, and what they can observe in your specific deployment environment. What are their bounds?
Okay.
Most organizations have never actually written this down. They just assume a generalized bad guy.
But why is the physical act of writing it down so critical? I mean, security engineers know what hackers do.
Because an unwritten assumption cannot be audited. People audit their security controls all the time. They check if the firewall is on, if the monitor is logging, if the sandbox is active. But those controls are just proofs within a model. They will pass the audit if the underlying model is assumed to be true.
Oh, I see.
The truly dangerous question is which assumption in your unwritten adversary model is doing the most work to keep you safe, and what happens when that assumption is false.
Let's play that out with a scenario. Give me an example of an unwritten assumption failing.
Let's say you are evaluating a new AI model for safety before deployment. Your unwritten assumption is that the adversary, the attacker, trying to bypass your safety checks, only has read access to the public API.
Right. Pretty standard assumption.
So you build all your defenses around rate limiting the API and filtering the prompts. But what if the adversary actually has write access to your evaluation benchmark? What if they subtly altered the test data your AI uses to prove it safe?
Oh, then your AI passes the safety test with flying colors because the test itself was rigged to let the malicious behavior slip through, and you would never even think to check the integrity of the benchmark because you assumed the adversary couldn't reach it.
Exactly the problem. If you don't write down that assumption, the adversary cannot write to the evaluation benchmark. Nobody will ever review it. It cannot be versioned alongside your software.
Yeah.
And most dangerously, it cannot be found to be wrong by a colleague who might know better.
Right, they can't review what isn't there.
And you must date it, because the environment and the capabilities of these models are moving at lightning speed. An assumption that was perfectly safe and bounded in March might be a fatal unbounded flaw in August. Write it down. Date it. Bound your adversary.
That is such a clarifying way to look at security hygiene. Stop obsessing over checking the locks on the doors and start checking the blueprint of the house to make sure you didn't assume a wall existed where there is actually just empty space.
If we connect this need for rigorous bounded defense to the bigger picture, it leads to a rather profound realization about the trajectory we are currently on with AI acceleration. There is a very common assumption in the tech industry that as AI gets smarter and faster, it will uniformly accelerate both attackers and defenders. A rising tide lifts all boats.
Right. The logic is that, yes, the AI will help the hacker write a zero-day exploit faster, but the AI will also help the security team find and patch the vulnerability just as fast. It sounds perfectly balanced.
It sounds balanced in theory, but in practice, they do not benefit equally from that acceleration. And the reason comes down to the fundamental mathematical asymmetry of what offense and defense actually are.
Let's lay that out, because this asymmetry is the core thought I want our listeners to really mull over. Let's look at offense first. An exploit and offensive action is an existential claim. It's essentially saying there exists a flaw in this specific state. And the terrifying thing about an existential claim is that it carries its own witness.
Yes. It only has to work once.
Exactly. You run the exploit, it either crashes the system or steals the data, boom, verified. The proof is entirely in the execution. You don't need to understand the whole system, you just need to find one crack.
A fence is essentially a search problem with a cheap mechanical oracle. AI is incredibly profoundly good at automated search. Constraint, solving semantic fuzzing, searching a vast state space for a single vulnerable gadget AI, accelerates all of this exponentially because success is self-verifying. The AI cries a million permutations, one works, and the job is done.
But defense is a universal claim. You are trying to prove that for all possible inputs across all possible states, this bad behavior does not occur.
Yeah.
You can't verify that from inside the system. You have to prove a property against an abstract model of the system.
And while AI can certainly help you verify properties within your model faster place, constructing the model itself is not a simple search problem. Deciding what the adversary can observe, noticing that a physical hardware flaw exists outside your logical software model, figuring out that two different parsers might read a single file differently that requires judgment, that requires understanding the gap between your abstract model and the messy physical reality of the deployed environment.
Right.
AI cannot automatically search for a flaw in a model that it doesn't know it's supposed to be looking at.
So as AI uniformly accelerates capabilities across the board, which side of that equation actually speeds up faster? The offense, which just needs to use an unbounded AI search to find one single self-verifying existential crack. Or the defense, which has to use human judgment and AI to universally prove the crack doesn't exist across an ever-expanding, ever more complex attack surface.
The math heavily, almost exclusively favors the existential search. The defense's true bottleneck was never in the part of the process that AI speeds up most effectively.
You know, we started this deep dive talking about that pristine whiteboard where AI math researchers do their work. It's clean, it's elegant, it's perfectly categorized. But out here in the real world, when you step off that whiteboard and plug that brilliant AI into a multi-tenant cloud network, the environment is hostile. The features we built to make the machine mathematically brilliant, the unbounded search, the cross-domain, bridging the abstraction shift, they are the exact same features that make it a weapon. Same object, relabeled objective. So the question to leave you with isn't whether the machine is smart enough to solve the proof. The question is who wrote the axioms it's trying to prove.